Okay, we're going to talk about arc length line integrals because, for example, we could have some wire and we may want to compute the mass of the wire. And it turns out that the mass will be some density, of course, times the arc length. And then it will be a line integral around that curve. So we'll need to know how to do arc length line integrals. The reality is, it's pretty similar to previous line integrals. We covered before how to do line integrals involving dot products and line integrals involving functions and where you just have some single differential. And how you do these, of course, is you just write this in terms of t using cancellation. And with arc length, it'll be something very similar. I'll put a row here. It'll just be ds dt times dt. And our ds, it'll be given by dx squared plus dy squared plus dz squared. Let me just, again, look at the 2D situation. If you want the arc length, you decompose it into vertical and horizontal and use Pythagorean theorem. So dx horizontal, dy is vertical, ds is the hypotenuse. So dx squared plus dy squared is ds squared. And in 3D, the arc length is similar. You just add a dz squared. So that means that ds squared dt squared, you just divide everything. So this is x prime plus y prime plus z prime squared. So if you, then this just means that ds dt is the square root of x prime squared, y prime squared, z prime squared. So you just add this thing, add to your integral. And then you just integrate like any other 1D integral involving t. So let's give an example of how to do one of these things. So let's consider the integral of x times y times z ds, where c is given by this curve. It's a helix. X equals sine of t, y equals t, and z equals negative cosine t. And it's a helix that, you don't need to draw this, but it's kind of fun to see what's actually going on here. Really, I think it looks sort of like this. It goes off in the y direction. So I would say it's a physically realistic curve, so it's worth knowing how to do this thing. And the t interval we're given is 0 to pi. Okay, and so to do this, we just follow the standard recipe of writing ds equals ds dt times dt, so we just need to know this ds dt. We know this is just the square root of x prime squared, y prime squared, z prime squared, so we just need x prime, y prime, and z prime. So x prime is just cosine, y prime is 1, and z prime is plus sine of t. So that means our sum of squares is cosine squared plus 1 plus sine squared, so that's just square root of 2. So now our integral over c of x, y, z ds is just an integral from, well, let's go back to our time integrals. It's just 0 to pi, and then we plug in x, y, z. So cosine t times, I'm sorry, I was plugging in x prime. Let me plug in x. So it is sine of t times negative cosine t. And then our ds is just square root of 2 dt. Okay, I'm just going to combine these two things. This should give me negative 1/2 sine of 2t by the double angle rule. So we just need to evaluate negative 1/2 integral from 0 to pi of t sine of 2t. So I would just use the integration by parts. So integral from 0 to pi t sine of 2t. If you use integration by parts, you should get negative 1/2 t cosine 2t if you integrate the sine term. And then minus that thing differentiated, the t. So cosine 2t. And this will be 0. Let's just really quickly draw cosine of 2t. So this will be pi over 2. Pi over 4, actually, if we draw in cosine 2t. We speed time up, and this will be pi over 2. And then, of course, this will be pi, 3 pi over 4. So then this, of course, will be pi. Okay, so all these will cancel. The negative area will cancel with the positive area. So in other words, we're integrating over a full period. So we just get negative pi over 2 times cosine of 2 pi. So it looks like we just get negative pi over 2. Okay, so in conclusion, we get pi over 4. Okay, let's do another example. I think a big class of examples comes from interpreting the center of mass of a wire as a line integral. So if you have some weird looking wire, you can ask where is the center of mass in x and y. And this is a physically meaningful question. In general, we just write, it's very similar to how you do the center of mass of a region, right? Because if we have some region, then x bar will just be 1 over the mass times the integral of x times dm. And this, of course, is our density times dA. So it'll be the exact same thing. So we integrate x, y, or z times dm, and in this case, our dm is just our density times the arc length. Okay? Let's see an example of how to do this. So let's find the center of mass of a wire in a helical shape x equals sine of t, y equals cosine of t, z equals t on the time interval t from 0 to 2 pi. And the density is constant k. So it's a normal wire, not some weird wire. So to get the mass, well, the mass will just be the integral of dm, in other words, rho times ds. And so we just need ds, because remember, rho is just k. So ds, again, is just that square root thing. So it's x prime squared plus y prime squared plus z prime squared. So if we write out x prime, that's cosine, y prime is minus sine, and z prime is 1. So we should just get cosine squared plus sine squared plus 1. So it's, again, the square root of 2 dt. Okay, so this is the square root of 2. So our integral now goes from 0 to 2 pi of k times the square root of 2 dt. So we should just get 2 pi k square root of 2 for our mass. Okay? Now, Let me just do x. Let me do z bar. So z bar, it'll just be the same thing with z. So it's c z dm. So you could just think of it as the same integral as before, but now you just use z. So if I write down the same integral as I did and leave some space, this is k root 2 dt. Now I just want my z in here, so I'm going to put a t. So I should get 1/2 2 pi squared times k root 2. That should be my z. Oh, I'm sorry. I need to divide by the m. So let me just put that m on the outside right here, and we can divide it at the end. So I'm going to go up top here so you can see what's going on below. So that means z bar looks like 2 pi squared k root 2 divided by m. So it looks like 2 pi squared k root 2 divided by 2 pi k root 2. We have to cancel some stuff. It looks to me like this is just pi. And then x bar and y bar will both be 0. And you can see this by symmetry, because if we have constant density, and if you just look at what's going on in the xy plane, it's just a circle. So the center of mass of that should be the origin. And so the z part will have something similar. And you can also just look at what's going on in the integral. If I put a cosine t here, surely the integral over 0 to 2 pi is 0. If I put a sine t, it'll also be 0 by cancellation. Okay, let me just do one more example. So in this case, you have to do the parameterization yourself, but we'll do something that's simple. So find the mass and the center of mass of a semicircle shaped wire given by x squared plus y squared equals 1 on the region x greater than or equal to 0. That makes it a semicircle, and the density of constant k. So if we draw that semicircle, here will be our wire, and we'll call it a curve C. And I think it's worth parameterizing t as the angle. So it should go from negative pi over 2 to pi over 2. And because a reason that angle is a good choice is that now we can let x equal cosine t and y equal sine t. Okay, so to get the arc length, we just need x prime, which is minus sine, y prime, which will be cosine. And so ds will just be the square root of sine squared plus cosine squared. So it'll just be dt. Okay, so the mass will just be the integral of k times ds. Remember that's rho ds, that's dm. So it'll be the integral from minus pi over 2 to pi over 2 of k times dt, so it looks like k pi. So now x bar, I'm going to stick that m in front just to avoid 1 over m appearing everywhere. Mx bar will be the same exact thing, but with x. So I'm going to write down my integral exactly the same way, leave some room, and now I'm going to write x in red. So x is cosine of t. So we should get sine of t times k, evaluated from minus pi over 2 to pi over 2. So it looks like this will be 2 times k, because sine of pi over 2 should be 1. Now, that of course means that our x bar will be 2k over m. So it'll be 2k over k pi, so it looks like 2 divided by pi. So when we just indicate where the x part is, it'll be closer to the origin. And that kind of makes sense because it seems as though more of the masses will be concentrated closer to the origin because it's flatter near y. But I'm sorry, more of the mass should be concentrated elsewhere. Right, 2 divided by pi is around 2/3, right? So well, I'm just going to draw it around here. Okay, now let's just do y bar. Actually, from this picture, you would think that y bar will be 0. And just to see why, you set up the integral exactly as before, and you add that sign of t, and now we see there's cancellation because the negative area will cancel with the positive area. Okay, so the center of mass will then be 2 over pi, comma 0, with mass k pi. Okay, thanks for watching.